So when we are solving log equations, we have to decide which of our two different types of log equations we are dealing with, right? It's important to use the correct strategy for the right kind of example or log, okay? So all log functions are one-to-one, right? They are graphed like this. Let's see if I can do a quick sketch of a log function. So there's my x and my y axis. There is, of course, a vertical asymptote that runs through the y-axis. The y-intercept, or rather the x-intercept, is at +1, and the graph hugs your asymptote and then graphs over like that. Okay, so if a function is one-to-one, it passes the horizontal line test. So I can draw any type of a horizontal line anywhere on here, and it only crosses your graph at exactly one place. Okay, therefore it's one-to-one. So every log has to be unique. Okay, that's what it says. Every log is unique. Notice that a log can't be negative, right? We can't take the log of a negative x. That doesn't exist. Okay, that will come up in today's notes here about negative logs. So notice here we have log base 4 equals another log base 4. So according to the one-to-one property, if these logs are truly equal, then whatever's in this parenthesis has to be equal to whatever is in that parenthesis, right? It has to be because they're equal. When things are equal, all of their parts have to be the exact same, right? We have log, check, log, those are the same. We have a base 4, base 4. So whatever is in my parentheses, which is 2x plus 4, that has to be equal to 10. Right, so we're going to solve this little equation for x, and we're going to figure out what value makes these two equations equal. So hopefully this is not any mathematical difficulty. We can subtract 4 from both sides. 10 minus 4 is 6. Divide both sides by the coefficient, and my x value would be 3. So if x is 3, right, 2 times 3, that's 6. 6 plus 4 is 10. Sure enough, log of 4 of 10 is the same thing as log base 4 of 10. Okay, that's basically all there is to it. So let's see what else we can do. So that is basically the one property we're using for everything. Okay, but notice in this problem there are how many logs on the left? 2 of them, right? And that's too many. There's log base 3 of x, and there's log base 3 of x minus 4. So we're going to apply the property that says if I am adding logs together, I can change addition to multiplication. I'm going to multiply these two arguments together. If I am adding the logs, that means I can multiply their arguments and condense it under one log. Okay, the verbiage is condense. So we're condensing this logarithmic addition problem into a single log multiplication problem. When we add logs together, that is the same as multiplying their arguments. So now I only have one log on the left, and I have one log on the right, which is exactly what I want. So my equation is going to be this thing has to equal that thing. And that's how I get rid of my logs, is I apply that property, the one-to-one property. So the left argument needs to be equal to the right argument. And of course, I distributed x times x and x times minus 4 to get x squared minus 4x. Now, if we'll notice, I have a squared term, I have a variable term, and I have a constant term. So this should remind you to create what type of an equation. And we do that by bringing our 12 onto the same side as all the other terms. So we create the quadratic x squared minus 4x minus 12 equals 0. Okay, and if you've been paying attention at all this year, you should know that we solve this by factoring. We're going to factor this. So in our brains think, okay, what numbers multiply to give me negative 12? Right, that's the last term of your constant. And at the same time, add to give negative 4. So we're looking for multipliers of negative 12 that also add to give negative 4. And hopefully your brain is going to negative 6 and positive 2. Negative 6 and positive 2 are the numbers that multiply to give you negative 12 and add to give negative 4. So I can rewrite my quadratic from standard form to factored form. X minus 6 and x plus 2 multiply together to give you 0. Okay, a quadratic. So that means that if the product of those two things is 0, either your first factor equals 0 or your second factor equals 0. All right, so we solve these both, and we get positive 6 as one solution and negative 2 as our other. But because we have logarithms, right, and we can't take the log of a negative, we have to do some testing. What happens if I plug positive 6 back into my equation? I get log of 6, that's okay, and log of 2. Right? Neither one of those things are negative, so positive 6 seems to work. But what about negative 2? What if I plug negative 2 into here? That's log of negative 2 and also log of negative 6. In other words, that can't happen. So negative 2, even though it was an answer to your quadratic, it is not a solution to your logarithm. Only positive 6 is a solution. So with these ones, you have to check, does this give you a negative log? And if it does give you a negative log, then it's not a solution to your problem. Okay, so we're condensing. Anytime there is a plus or a minus, you have to condense first. So here we have another problem where I see that there's a minus, right? So I have to once again condense these subtraction of logs into one single log. So what property do we use condense has an N in it? Condense. Subtraction becomes division. Excellent. So this is the log of the first argument, 2x plus 4, divided by the second argument, x minus 3. Okay, so we're using all those properties that we talked about last week for like a day, maybe even half a day. Not very much. Okay, to condense these so we can solve. Because now that we have log equals log, right, we can basically take away the logs and solve. So I have a fraction equals a number. How do we deal with a fraction equals a number? We turn the number into a fraction. So fraction equals fraction, and now we cross multiply. Okay, so we cross multiply. We do 2x plus 4 times 1, which is 2x plus 4. And we do x minus 3 times 3. Okay, so we have to distribute the 3 into the x, and I get 3x minus 9. Okay, so make sure you're using parentheses so that you're distributing that numerator into both of those things, right? It doesn't go into just one or the other. And now let's solve. So I'm going to minus the 2x to the right side because that keeps x positive. And then I'm going to add the 9 to the left side to get x by itself. So x equals 13. So let's check. Does this give me a positive number? Yes, 2 times 13 plus 4 is a positive number for sure. And what about over here? 13 minus 3, yes, that's positive 10. Sure enough, 13 is a viable answer for us. Okay, so when we have multiple logs, you have to use the properties to condense them. Addition becomes multiplication, subtraction becomes division. So let's look at the other style. Okay, if the equation has only one log, so this is a whole different family of equations. So we're going to see log of something equals a number. Right? You're only going to have log on one side of your equation equals a number. Okay, so if that's the case, we do things differently. We take our log and we rewrite it as an exponential. Okay, so we use that formula where the base of your log becomes the base of your exponential. The answer for your log becomes the exponent for your exponential, and the argument of your log becomes your answer. Okay, so we're rearranging the furniture when you have log equals number. So example 4, that's exactly what we have. Log equals number. So this becomes the base of your exponent. This becomes the exponent of your exponential, and that needs to equal x plus 5, the argument of your log. Okay, so these ones might be a little bit trickier, maybe, but the first thing we need to do is evaluate this number, 2 to the third power, which means 2 times 2 times 2. 2 times 2 times 2 is 8, equals x plus 5. So when I subtract 5 from both sides, I get a value of 3. Okay, and plugging it in, sure enough, 3 plus 5 is 8. That is a positive number, and 2 to the third does in fact equal 8. So here on example 5, hopefully you're noticing that there is a plus between your logs. And anytime we have a plus between your logs or a minus, we need to use the properties to condense this down. Okay, addition becomes multiplication. So this is x minus 3 times x plus 3 equals 2, right? Because we want it in the form log of an argument equals a number, right? Log equals number. That's the form that we want when logs are only on one side of your equation equals a number. Okay, so this is what we do if we have a number over here, or basically anywhere in your problem. If you don't have everything that's a log, then you have to solve it like this. So let's rewrite it. 5 becomes the base of your exponential. 2 becomes the exponent of your exponential. And then let's multiply this out. X times x is x squared. X times 3 is 3x. Negative 3x down here, and a negative 9. So when I combine my like terms, a positive 3 and a negative 3 subtract each other out, and I'm just left with x squared minus 9. Okay, x minus 3 times x plus 3 simplifies to x squared minus 9. Okay, so let's evaluate 5 squared. 5 squared is 25. 5 times 5 is 25. Equals x squared minus 9. Okay, let's add our 9 to both sides to get the variable by itself. 34 equals x squared. And your last step is to square root. Okay, now just as a formality to remind yourself, when we take the square roots in algebra, when we're solving, you have to get positive and negative numbers. So x is the positive square root of 34 and the negative square root of 34. But hopefully we've learned so far that if it's a negative, then this is going to be a negative value. So we cannot use the negative answer as part of our solution. So the only real solution is the positive one, x equals positive root 34. So we are condensing logs so that there's only one of them, right, using the properties of logs. So our last one is kind of tricky, because notice there's log on both sides, right? We have log over here and log over there, but there's this pesky little number. Okay, so we want to make log equals number, so I have to take this log and move it over to that side. Right, because I want the logs on the same side. So I have a plus here. What's the opposite of plus? minus. So I'm going to subtract this from both sides. Okay, I am subtracting the log. So that ends up looking like log of x minus 5 minus the log of x minus 4, because you don't actually subtract them, right? We just write them down next to each other like neighbors, equals 1. Okay, log equals number. So now I can take that property that says minus becomes division. X minus 5 over x minus 4, and I still have log out here equals 1. Okay, log equals number. So now I'm going to take this and rewrite it as an exponential, but I don't see a base. So here's the next question. What is the base of a log when you don't see a number? And the answer is 10. Excellent job, students. We're so smart. Log base 10. So this becomes the base of my exponent, 10 raised to the first power equals this fraction, x minus 5 over x minus 4. Okay, so I go ahead and make this into a fraction by dividing by 1, and then I cross multiply x minus 4 times 10 and 1 times x minus 5. Okay, fraction equals a number, so I change it into fraction equals a fraction. So 10 times x minus 4 equals x minus 5. Okay, so I can distribute in here, and I got 10x minus 40 equals x minus 5. Right? I'll bring the x to the left side. I'll subtract it. I'm going to add 40 to over there. 9x equals 35. Okay, so I'm solving this equation for x, and I divide both sides by 9. And if I look into my calculator, this number is 3.8889. Okay, which is a great positive number, right? It's a pretty good number. But once again, we have to investigate. Is this number an actual solution? Okay, and of course, I probably wouldn't ask that question if it were, right? Because when I plug 3.8 back in there, what's 3.8889 minus 5? Right? I don't know, but I know that it's negative. That number is less than 0, right? Negative 1. So I don't want to do that, right? Negative 1 and change, which is negative. So, does this actually work? No, it doesn't. So this one actually has no solution. Even though we got a positive answer, when we plug that back into our logarithm, it does not give us a positive value. And you have to have a positive argument for your log. Okay, so we're using properties of logs to condense your problems before you solve for x. Thanks. Okay, that's all. Goodbye.